Okay, for this exercise question, this is a heat equation. The boundary condition we have in terms of del U, del X. Okay, and here is the initial condition. So as usual, we have the PDE. PDE we have to transform becomes ODE using U equal to XT. We have the boundary condition. Also, we have to transform it using U equal to XT. So if you try this, I think you will get the equation x double prime minus lambda x equal to 0. Okay, the same actually for all heat equation. It will lead to the same things. Okay, but you have to know how to get from this PDE using this becoming these two ODEs. For the equation for T here will be 1 over T dt equal to lambda. Okay, so the boundary condition here also you have to use this transform again. You can check the answer. It should be x prime at point 0 equal to 0, x prime at point 2 equal to 0. And here the initial condition we will use after we sum all the three solutions. Okay, so we solve the equation for x first together with the two boundary conditions. You will get for case 1. Okay, so here is a boundary condition of this type. You will get case 1 non-zero for solution x. So you have to proceed solving equation for t. You will get a solution for case 1 equal to constant. For case 2, x solution is 0. So case 3, you will get solution for x non-zero. Okay, so when you sum all solutions and then you use the initial condition here, you will get it in the form of even Fourier series. So all the unknowns that appear, you can use the formula for the even Fourier series. Okay, will lead to this answer. Okay, I proceed with next is the wave equation. Okay, so for wave equation, we have seen wave equation in the D'Alembert method. Okay, so it's actually equation. This is the equation for the wave equation. There is the second derivative of u with respect to t. There will be a constant. There will be on the right second order derivative with respect to x. Okay, 0 to L here is the length. The problem here is U represent the vertical displacement of elastic string. Okay, so X here represent the length of the string. Okay, 0 to L. T is time. Okay, so the problem can be represented as this partial differential equation. So the boundary conditions, it can be boundary condition in terms of U or UX as well at both ends of the string. Okay, similar with the rod, we have the condition at the first point and the last point. Okay, so the problem here different with the D'Alembert method. D'Alembert method we apply if we have the long string, okay, minus infinity to infinity. But now we have the finite value for this string, so we have certain length for it. Okay, so we can solve this case by using the method of separation of variables. There will be also the initial condition. So this will be different with the heat equation. To get the complete solution for wave equation, we will need two initial condition. Okay. So example here 3.2 for wave equation, solve the following PDE. So the process actually is still the same. Okay, see here. This is PDE. PDE having the second derivative both, okay, on the left and right hand side. about the boundary. This is boundary condition. This is initial condition. See, we have two initial conditions. Okay. So solving process, first we use u equal to xt into the PDE. So in this PDE, see on the left we have del square u del t square, different with the heat equation. So means from u equal to xt, now we have to find del square u del t square. Okay, means we have to differentiate this u with respect to t twice. Okay, so means on the right here, only t terms we differentiate twice. So we have xt double prime. Okay, the right hand side, I think we have seen in the heat equation. We differentiate u with respect to x twice. Okay, so only x differentiated twice. So now this from this PDE, the left hand side becomes xt double prime. The right hand side becomes 4, differentiate x twice, so x double prime t. Separate x and t, make it equal lambda. So in this case, let's say usually for the constant here, we bring together with t. So we have t double prime over 4t equal to x double prime over x equal to lambda. So if we consider x only, we will have equal to lambda, we will have the ODE for x. So we have x double prime over x equal lambda. We will get the equation for x, x double prime minus lambda x equal to 0. And if we consider equation for t only, we will have t double prime over 4t equal to lambda. So for wave equation, in its ODE, there will be difference for its T equation. Heat equation, we have first order. Wave equation, we have second order ODE for T and also for X. So this will becomes T double prime minus 4 lambda T equal 0. Okay, so both are second order ODE. For the boundary condition, we have to change as well. Okay, I think this is simple. This clearly we can see the value for x is 0. Okay, it depends on the condition. Here condition is u, so we can use this u as it is. So x 0 t, the first condition like this. After we replace, so we get x 0 equal to 0. For the second condition, we have x at point 3 multiply with t equal to 0. So we get the second condition is x3 equal to 0. Okay, so we have two ODEs. We have boundary condition for x. So we proceed with the next step, solving the ODE for the three cases. Okay, I write the ODE that we have. We have x double prime minus lambda x equals 0. We have t double prime minus 4 lambda t equals 0. We have conditions for x. x 0 equals 0. x3 equals 0. So we have to solve ODE for x first for each case here. Okay. So I think it will be the same as in the previous example. Okay, for this part. Okay, so if lambda equal to 0, we get x double prime equals 0. So the full explanation, you can go back to the previous example. It's the same actually, because I choose, okay, the boundary condition the same, right? Okay, so we have x equal to ax plus b. So as usual, after we substitute the boundary conditions here, we get the solution equal to 0, x equal to 0. So for this case, we don't have to solve equation 40. We already get the solution for the first case here, x multiplied with t equal to 0. Okay, make sure you know how to get this, because sometimes in answering questions during final, there will be marks given for the steps you do. Okay, so for lambda equal to positive p square, we have x double prime minus p square x equals 0. Again, this is actually the same as we see in the previous steps, previous examples. Okay, where it leads after we solve the second order ODE here, we use the boundary condition here, you will get the solution x equal to 0. So for the second case also here, u equal to xt becomes 0. And for the third case, lambda equal to negative p square. Okay, also I think also the same as in the heat equation that we see. We need to solve x double prime plus p square x equal to 0. So you solve this, the second order ODE, using the boundary condition, you will get for this case x equal to e cos px plus f sin px. Okay, so again, after you substitute the condition, x0 equal to 0, so here is 0 equal to e. Okay, the first condition, x0, so we have cos 0 is 0, cos 0 is 1, sin 0 is 0, so we have e equals 0. The second condition, we have 0 equal e cos 3p plus f sin 3p. Okay, so e is equal to 0, so we can eliminate this. From here we have this, so sin 3p equal to sin n pi equal to 0, so we can conclude that p equal to n pi over 3. Okay, full explanation has been given in the previous examples. So from here, the case here, the solution for x is non-zero, which is equal to f sin 3 n pi x over 3. Sorry, sin n pi x over 3. Okay, so the solution exists. We have to proceed by solving the equation for t. For this case, negative p square. So the equation is this one. So replace, we will have t double prime minus plus 4p square t equals 0.